We're back to 2.7, and I'm going to introduce another definition of the derivative at x equals a. So in your book, this is definition 2 and 4. Let's take a look at this. M, or the slope exactly of the tangent line x equals a, is the limit as h goes to 0, f of a plus h minus f of a over h. So it looks different, but it actually is just kind of renaming some things in our definition we went over. So let's see how that works. This is example 1 that we already just did. The difference is that we're going to use this new definition, and all the things you see in orange are things that are going to connect what we did with our old definition and this new one. So first of all, we have our point a f of a. That's the same. Over here I'll point it out right there. And then we're going to rename our point x f of x, which I'm pointing to here, as a plus h, comma, f of a plus h. So how does that work? Well, let's define h as some small distance from a, which is an x coordinate, and the place for which we're trying to figure out the slope of the tangent line. And so then a plus h makes sense in that we could just have some other point on the graph be there. If h is negative, the point will be to the left. Go down and look at our blue right triangle, and I'll point it out here, that instead of that base of that triangle being x minus a, now that we define this point as a plus h, it would be a plus h minus a, which is just h, or you could just define it as h in the beginning, noting that we have some base of the triangle that is some small value h. And again, if this point were to the left, it would be a negative h. Alright, well, then the change in y, or the height of the right triangle here that's in blue, would be, instead of f of x minus f of a, it's going to be f of a plus h minus f of a. So we're just redefining this little slope formula here. And then because we're not taking the limit as x goes to a anymore, notice we're going to have h go to 0. And h is going to go to 0 every time, because if we define it in this way like we have, then we want to let the h go to 0, because that means that the points with the secant line are getting infinitely close to our point p at a f of a. So in terms of the limit, notice that the limit as h goes to 0 part does not change. It is always h going to 0. So that's one nice thing. And then we have a little bit different formulation here, f of a plus h minus f of a over h. So that h is like the delta x, and the f of a plus h minus f of a is the change in y. So let's go ahead and do this example now with this new definition. So f of a plus h, well, first of all, maybe you want to plug in your a again, but notice it's not part of the limit anymore in terms of, you know, where you're taking the limit. It's going into the function, however, still. Negative 1 plus h. h is what the limit depends on, so that's a good thing that you're not plugging anything in for h, it's just h. Then your f of a is as before, it's just f of negative 1. So you could either do that as side work or plug it in to the formula and handle it there. And then this is over h. So taking this a step further, let's go ahead and use the function now. So remember, when you plug something kind of complicated into a function, that it's like you're replacing x with negative 1 plus h in this case. So you might want to use some parentheses even to see this. It's like parentheses minus parentheses squared, where inside the parentheses you put negative 1 plus h. So this right here is just the f of negative 1 plus h. And you really got to get used to plugging that in and doing that properly, because it's another important thing that we're going to have to do in 2.8. Minus f of negative 1, again, you could do it as side work or just plug it in here. And so that's going to be -1 minus the quantity -1 squared. Alright, so the plug-in part is a little bit harder than our last definition, but this thing is going to bear fruit at the end, and it's going to be a little bit easier on the tail end. Alrighty, so now what you want to do with this first part is just kind of simplify when you can, or I shouldn't say simplify, but expand. So -1 plus h, I can drop those parentheses. I'm going to keep the minus up front, but I'm going to expand the square thing. So I'm going to have 1 minus 2h plus h squared. And then we're going to have the plus 2 again. This is all over h. So keep on simplifying a little bit here and distribute that minus, for example. Also, you can start combining some like terms if you wanted to. Keep this limit notation throughout because we haven't attempted to take the limit yet. Alright, now notice that you can combine some like terms up top. And -1 minus 1 plus 2 is 0. We also have an h plus 2h, which is 3h. And what else do we have? Just a minus h squared. Just a quick aside here. If you try to plug in h equals 0, implies you get 0 over 0. So just like with the last definition, you always get this indeterminate form, 0 over 0, if you just try to plug in h equals 0. So you're going to have to do some algebra, but here is the benefit of dealing with that more complicated version in the beginning, with that a plus h, having to plug that into the function. Now notice this thing is easier to cancel factors. The problem child is h equals 0, or h for h equals 0. So just factor out the GCF on top. It's an h. If it's not an h, you screwed up. Go back, figure out what you did wrong. h's cancel, and so now we just have to plug in h equals 0 to this equivalent function that's defined at h equals 0. So 3 minus 0 is 3, and we got the same answer as with the limit definition, the definition of a derivative at x equals a, with the limit as x goes to a. So know both definitions, but this second one that I'm going over right now is the one that you'll want to know the best.